Hi friends, do you know what makes these toy cars move? That's right, there's an electric motor in this car. Electric motors are used in many places, such as these toys, fans, washing machines, mixers and grinders. In this video, we look inside the electric motor and see how it works. The electric motor is based on the principle that if you place a current-carrying conductor in a magnetic field, then the conductor will experience a force. We are going to discuss this principle and see how it is used to design the electric motor. And after you watch this video, try solving the quiz and the top 3 questions on this topic. Links are given below the video. In an earlier video, we have discussed about the magnetic effect of electric current. That is, a current-carrying wire produces a magnetic field around it. If we place a magnetic compass near a current-carrying wire, the compass will get deflected. A magnetic compass is made of a tiny magnet. So we can say that a current-carrying wire exerts a force on a magnet. Now let me ask you, is the reverse also true? So can a magnet exert a force on a current-carrying wire? That's right. The answer is yes. And if the wire is free to move, it will produce motion in the wire. This is expected because remember Newton's third law? To every action, there is an equal and opposite reaction. So if a current-carrying wire exerts a force on a magnet, the magnet will exert an equal and opposite force on the current-carrying wire. Another way to understand this behavior is, we know that a current-carrying wire behaves like a magnet. So when a current-carrying wire is kept near a magnet, it's like keeping 2 magnets near each other. Naturally, the 2 magnets will attract or repel each other. So there will be a force between the current-carrying wire and the magnet. This behavior, that a current-carrying conductor experiences a force when placed in a magnetic field, was observed in 1821 by Michael Faraday. If a conductor, a wire, is placed in a magnetic field like this, he observed that when you pass current in the wire, a force is exerted on the wire, which makes the wire move. When there is no current in the wire, there is no force. Another interesting observation is that the maximum force is experienced when the current-carrying conductor is placed perpendicular to the magnetic field. But when the conductor is placed along the magnetic field, that is parallel to the magnetic field, then the force on the conductor is 0. And if the current-carrying conductor is placed at an angle to the magnetic field, it will experience a force. But to get the maximum force, the conductor should be placed perpendicular to the magnetic field. Let's place this important principle on our concept board, that a current-carrying conductor placed in a magnetic field experiences a force. When a conductor is placed perpendicular to the magnetic field, the magnitude of the force on the current-carrying conductor depends on 3 factors. The force is directly proportional to the strength of the magnetic field, which is marked as B. The force is directly proportional to the current I flowing in the wire. And the force is directly proportional to the length of the wire L, which is present in the magnetic field. Now combining these 3 factors, we get force is directly proportional to BIL. To change the directly proportional relation to an equation, we need to add a constant K. So we get F equal to K into BIL. Now the value of the constant K depends on the choice of units used. In SI units, K is equal to 1. So the formula becomes F equal to BIL. And it's easy to remember, force equal to Bil. And you can remember the 3 factors right from this formula. B is the strength of the magnetic field, I is the current, and L is the length of the conductor. Now, what is the SI unit of magnetic field? If we use this formula, we can derive the unit. P is equal to F divided by I into L. So, the SI unit of B is equal to Newton by ampere meter. Now, do you know what is the name given to this unit, Newton by ampere meter? That's right, Tesla, and the symbol is T. Magnetic field can also be measured in terms of another unit, Weber per meter square. Let's put the three factors affecting the magnitude of the force on a current carrying conductor placed in a magnetic field on our concept board. We know the factors affecting the magnitude of the force. Now let's talk about the direction of the force on the current carrying conductor when it is placed perpendicular to a magnetic field. We can easily find the direction using a rule called Fleming's left-hand rule. For Fleming's left-hand rule, hold your left hand like this, with the forefinger, center finger and the thumb of your left hand at right angles to one another. The forefinger represents the direction of the magnetic field. It's easy to remember. F for field, F for forefinger. The center finger represents the direction of the current. You can remember it as C for current, C for center finger. And the thumb represents the direction of the force on the conductor. Let's see how we can use Fleming's left-hand rule to find the direction of the force on a current carrying conductor placed in a magnetic field like this. The trick is to consider each thing one by one. Let's start with the magnetic field. Remember, the magnetic field direction is from north to south. Forefinger is for the magnetic field. So hold the forefinger like this along the direction of the magnetic field. Next, let's look at the direction of current. One important thing to note is Fleming's left-hand rule uses the conventional direction of current, not the direction of flow of electrons. So keeping the forefinger aligned along the magnetic field, now align your center finger along the direction of conventional current. The center finger will point downwards. Now the thumb will automatically give you the direction of the force on the wire. As you can see, the direction of the force is outwards. So out of these three things, magnetic field, current and force, if the direction of two things are given to us, we can use Fleming's left-hand rule to easily find the direction of the third thing. Just remember to keep the three fingers at 90-degree angles to each other, and you may need to rotate your hand at the wrist in order to align with the question that is given to you. It may seem a bit difficult at first, but with practice, I'm sure you'll find it really easy. Let's go ahead and put Fleming's left-hand rule on our concept board. We have learned this important principle. When a current carrying conductor is placed in a magnetic field, it experiences a force. We can find the direction of the force using Fleming's left-hand rule. Now let's see how this principle can be applied to build an electric motor. As we discussed, electric motors are used in various things like this toy car, fan, mixer and grinder, washing machine and so on. An electric motor causes some kind of rotation. As you can see, an electric motor causes some kind of rotational motion. What form of energy does the electric motor use? That's right, electrical energy. And what form of energy does the electric motor convert it to? Correct, mechanical energy, or to be more specific, rotational kinetic energy, since the motor produces rotational motion. So an electric motor is a device that converts electrical energy to mechanical energy. We are going to discuss about the DC motor, the electric motor that works on direct current. Direct current means the current that flows only in one direction. For example, a cell is a source of direct current. We have seen that when a current carrying wire is placed in a magnetic field, the wire experiences a force. If the wire is free to move and the force is large enough, it will make the wire move in a certain direction. This is called linear or translational motion. But an electric motor produces rotational motion. How is the motor designed to produce rotational motion? Let's take a look at a simple example using a block. If I apply a force on this block, it moves in a certain direction. This is called linear or translational motion. But if we want rotational motion, you need to apply two forces. Now the block is rotating. In physics, this is called a couple. Two equal and opposite forces acting on a body forms a couple and produces rotational motion. An electric motor is designed based on this concept. Rather than using a straight wire, the wire is in the shape of a rectangular coil. So two equal and opposite forces act on the two sides of the coil to produce rotational motion. So a motor works on the principle that when a rectangular coil is placed in a magnetic field and current is passed through the coil, forces act on the coil, which rotates it continuously. To understand how a motor is made, let's go ahead and build it step by step. First, we need a magnetic field. The magnetic field is from the North Pole to the South Pole. Next, we need a rectangular coil made of insulated copper wire. We are going to place the rectangular coil in the magnetic field. This rectangular coil marked as ABCD is called the armature coil. To make sure the current in the coil flows in the right direction, we need a device called a commutator. The commutator contains two half rings made of copper, known as split rings. The two ends of the coil are joined, soldered to the two half rings of the commutator. The rectangular coil and commutator rings are mounted on a shaft and they rotate. Next, we need a voltage supply to run the motor. Since we are discussing a DC motor, the voltage supply is a battery containing one or more cells. If the wires coming from the battery are directly connected to the commutator, the wires will get twisted when the commutator rotates. To avoid this, we need carbon brushes. The carbon brushes maintain contact with the rotating commutator, and since they are good conductors of electricity, they allow current to flow through it and into the coil. Now that we know how an electric motor is made, let's analyze how it works. Let's say the rectangular coil ABCD is initially in the horizontal position. When the switch is turned on, current flows in the coil in the direction DCBA as shown here. Now let's focus on side AB. AB is a current carrying conductor placed in a magnetic field. So AB will experience a force. We can find the direction of the force using Fleming's left-hand rule. As you can see, the force on AB will be upwards. Now let's look at side CD. Again, we can apply Fleming's left-hand rule. The force on CD will be downwards. What will be the force on side BC? That's right. The force on side BC will be 0. Even though current is flowing through the side BC, but BC is along the magnetic field, so it will not experience any force. Similarly, the force on side AD will also be 0, since AD is also along the magnetic field. The equal and opposite forces on sides AB and CD form a couple and cause rotational motion. The coil rotates in a clockwise direction. While rotating, when the coil reaches a vertical position, the carbon brushes will lose contact with the commutator since there is a gap between the commutator rings. The current in the coil will get cut off, but the coil will continue rotating due to its inertia of motion. After half rotation, the side CD will go to the left side and side AB will move to the right side. And each commutator half ring will now touch the other carbon brush. This reverses the direction of current in the coil. The direction of force on side CD will now be upwards, and the direction of force on side AB will be downwards. Due to these two forces, the coil in the motor will continue to rotate in a clockwise direction. After every half rotation, the direction of current in the coil will get reversed, and the coil continuously rotates in a clockwise direction. This is how an electric motor works. Let's go ahead and put the DC motor on our concept board. Now we know what's inside an electric motor and how it works. Let's discuss what are the ways to increase the speed of rotation of the motor. Now, to increase the speed of the motor, the speed of rotation of the coil needs to be increased. How can we increase the rotation speed? For higher rotation speed, we need a greater force on the coil. And we had discussed the factors on which the force on a current carrying conductor placed in a magnetic field depends on. Remember the formula of force? F equal to BIL. So one way to increase the force and the rotation speed is to increase the strength of the magnetic field. Now this can be done by inserting a soft iron core within the coil. Another way to increase the rotation speed is to increase the strength of the current in the coil. And another way to increase the speed is to increase the length of the coil. To do this, we can increase the area of the coil and the number of turns in the coil. So there are 4 ways to increase the rotation speed of the motor, which is to increase the strength of the magnetic field, increase the current in the coil, increase the area of the coil, and increase the number of turns in the coil. Let's pin the ways to increase the speed of rotation of the electric motor on our concept board. I hope the concept of electric motor is crystal clear to you now. So next time when you switch on the fan or see a mixer or washing machine rotating, I want you to think about the electric motor that's rotating inside. And to revise these concepts, try the quiz and the top 3 questions for this video. To make it easy, I'll put the links below. So just click on the links and try the quiz and write your answers for the top 3 questions. And I promise to reply to your answers as soon as possible. And do remember to like, comment and share out this video. And if you haven't subscribed to my YouTube channel, hit the subscribe button right now. Also click on the bell icon to get notified about new videos. You can check my Facebook page and do check out my website manochaacademy.com for more videos like these and for the quiz and the top 3 questions on this video. Thanks for watching.